let's consider a simple circuit. If I have more batteries in series, the bulb gets brighter. I have more current flowing. The bigger the voltage, the bigger the push, the bigger the current. I also know that if I go down to the hardware store, I've got all different kinds of bulbs I can buy. I can buy a 40-watt bulb, I can buy a 100-watt bulb. And they glow differently. And I'll also find, if I use my ammeter, that I get a different flow through the tube. And so that means that not all bulbs have the same flow through them. The same push is going to give me different results depending on what I hook up. Now, in this class, on homework and on the exams, we will always use identical bulbs, made at the same factory by the same worker on the same day. But I talk about this to introduce the idea of resistance, which is futile. You know what this is, right? Okay, some geeks in here. This is the board, right? If you don't know about the board, there's a homework assignment for you. Okay, let's talk about resistance. Resistance is just that. How hard it is to get this charge to flow through something. Now, the way I measure resistance, thanks to Georg Ohm, is with this definition here. Set this current equal to 1, and that tells you what resistance is. If I want to know the resistance of this pen, what I would do is I would change the voltage difference across the pen. I would ramp that up bigger and bigger and bigger. And when that voltage difference was big enough to push 1 amp through the pen, that voltage difference would be my resistance. That's how I would define it. If you set the I that's passing through the pen equal to 1, then the resistance is equal to how many volts it takes to get that to go through. Now, for many materials, most materials, we find, I should say, this unit, volt per ampere, or volt per amp, we call the ohm to honor a dead professor, okay? And I just got to pause here and point out that you've seen a whole lot of really homely scientists. But that is one handsome-looking scientist. I think we'll all agree, right? He could be a count. Now, what we find is that many materials have a constant resistance regardless of how hot they are, or regardless of how many amps are flowing through them. And we call these materials ohmic. Now, when something is ohmic, we typically use this definition as a law, and it's called Ohm's law. V equals IR. Now, when I say V equals IR, I really mean delta V equals IR. And I can't say this law without chuckling a little bit. When I was an undergraduate, there were just 10 of us in our class. We took all the classes together, one after another, semester after semester, until we got to our senior year in quantum. And then there were 11 of us. And that's because there was one student, his name was Eric, and this was his 3rd or 4th time through quantum. He just never could get through that class. And I took it as my personal challenge to get him through that class. And it turns out the physics department didn't want him to graduate. They didn't want him to pass that class, because Eric was in charge of our electronics shop. And any broken equipment in any of the experiments, they brought to Eric, and he quickly fixed that. He could fix anything. Now, because I was trying to get him through this class, he was often at my house, late at night, working on homework. And I remember one night I was tired and I was just getting frustrated, and I said, Eric, buddy, it's not that hard. hard. I mean, you can fix all that electronics. That's hard. He says, oh, shucks, Greg. He's from Tennessee. Shucks, Greg. Electronics ain't hard. All you got to do when something's broken is you just shake your finger at it. And you say, V equals R, V equals R, V equals R. It turns out he's right. That is the secret to solving all electronics problems. V equals R, V equals R. This is the F equals MA of circuits. It solves every single problem. And it wasn't until years later that I finally realized that, dang, Eric was right. V equals R. Now, when you say that, it's really delta V equals R. Okay.